Penrose and everybody for inviting us here and this nice gathering of other mathematicians. I'm going to talk about, well, math's a huge topic. I have to, of course, constrain a bit. That about 100 years and inverse relativity, where Einstein wrote down the equations in 1915. And one thing I would like to do is the perspective of mathematics. First of all, the main issues, what's interesting about the main breakthroughs, let's say, in mathematics years. Of course, I'm not able to cover everything, so apologies to things that I cannot, which are great contributions, but just to point out a little bit about the different flavors of what math GR actually has been as a topic in the last 100 years. I'm going to talk mostly about, well, geometric analytic aspects and connect them to some recent questions and recent research in these fields. And at the end, if there is time, I'll talk a little bit about cosmological questions as well, but I will mainly talk about non-cosmological questions. So first, I mean, if you think a little bit, I'll give you a little bit of an introduction from the mathematical point of view of the relations had with the theory. So if you think about it, so in 1915, when Einstein wrote down the equation, so this was a hard struggle he had there. It's a very geometric equation, and they look nice, but if you would like to make, to work with them, it's kind of a subtle thing. So if you would like to solve an initial value problem, a Cauchy problem, it's not clear at all how to set it up first. So what's the initial data? How does the evolution look like? How should that be done? And so it's interesting that at the beginning, so it took really until in the 1950s until the initial completely understood, or at least it was the well-Posedness results by Choquebriand and Guéroche. A lot of things happened in between. It's interesting to see that, for instance, on the physical side, you have big things happen. So Eddington had the expedition where they caught the bending of light. In 1927 found that the universe must be expanded from. So there were all these breakthroughs. Basically, well, a lot was going on also, but there's the results were not yet there. So with it, just having a good. So what are the questions, or why is this? So some already used. And what about the existence and uniqueness? I mean, it's a mathematically important question. Physically, what what does it mean, etc. And the behavior solutions and even determinism in relativity are clear from at the beginning at all. So, for instance, at what speed does the gravitational field problem work that went into these directions? Of course, had some work here on gravity. Other people talking about unique existence of solutions is Stellmacher, and Yvon Choquebriand, of course, later. It's not clear, for instance, even how. Just the very early years. So, of course, everybody knows Einstein and Schwarzschild, known for the first solution. A little bit on the cosmological side, Einstein a cosmological term into his equations. So, meaning he was believed motion you only have on the small scale, but not on the large. Cosmology found a solution for the Einstein vacuum equations and in 1990, Arthur Eddington, this expedition that confirmed the bending of light, that convinced the universe is Alexander Friedman dynamical, so universe could end or collapse, so dynamical solution. They complained at first thought, found out, no, your solutions are right, but this is mathematical, this cannot be the physics. In 1927, so he found, again, dynamical solutions. Slipher's observations of what we nowadays know are galaxies, is nebulae, and they all were, most of them redshifted. And he combined these solutions with the redshifts in observation, expanding. So he was first to conclude the expansion of the universe, and he found even the velocity relation. Well, here this is what is called the Hubble constant. Actually, 2 years later, had a paper where he finds this relation, but he does not talk about the expansion of the universe. He might not believe. So that was, the last sentence is personal from communications with Alan Sanders. He was over from Hubble after Hubble. Anyway, Cauchy problem, there's more to say, but very brief highlights. Well, of course, for those who do not work in relativity here, at least once in the talk, I want to show the Einstein equations. On the left-hand side, we have curvature terms, the Ricci, the metric term, and the scalar curvature, and we're solving the Einstein equations for the metric here. On the right-hand side, if you have any matter or energy present, you have to provide also stress energy tensor and the corresponding equations. Let's say if you have electromagnetic field, you have the Einstein-Maxwell system here. And, I'm talking about four-dimensional relativity. Well, if you have Einstein vacuum, so that's if the right-hand side is 0, you don't have any matter, You have the Einstein vacuum equation, so your space-time Ricci is 0, but still interesting things can happen in this regime. Okay, well, going back to the constraints again and to early contributors, and again, so that the story is much richer. Of course, I'm giving you a talk here of 1 hour, not only about history, so I'm omitting many contributors. But something interesting is that in 1929, Darmois noticed that the existence of this GR constraint in the analytic setting. So you have a foliation with a time. So if you have Spacelike type of surface, you give initial data, which metric here, what's going to be the second fundamental form initially, and then you would like as an equation decoupling equations. So you would like to solve an initial value problem. So in the analytic case, so he looked at these constraints and found, well, there is the existence. These constraints actually exist and can be written. The metric can be written in this form. So and with this, so this is the analytic case where, for instance, this is not physical, right? You would not see any in an hour or so. So that's too much to ask for. Then Lichner also looked at the generalized here, but they knew that, well, you have to get away from the analyticity, of course. Okay. Well, the problem, the initial value problem, if you do a space-like value problem, so you have initial sets, as I just mentioned, you have a 3-fold, you have a G-bar, used metric on the initial surface. The symmetric 2 tensor cannot just specify drained equation. Well, the Cauchy development then, so is the evolution equations, and that will be globally hyperbolic, very rare, have an embedding from the initial hyperbole in the correct way. Well, embeddings in this case, so what I mean topically flat, it's that think of a galaxy, you can describe local with some curvature and geometric structure. So you think that far away that you're interested in has going on here, but it decays to flat Minkowski space affinity. And of course, it depends on, but topically flat. Well, here the constraint equations in the space-like set write down like that of my metric. And when I write the bar, this means the curvature on the. I introduced here, not in the cosmological setting. And interesting and important, these constraints propagate. In order to solve the Cauchy, ways to do that, I mean, you have some degrees of freedom in data, right? So you can choose, for instance, the trace of k to what we call a maximal slicing, so a maximal time function. For this work done by, Piotr Kruszell, who is here also, and Brodnik and Omershu, maximal slice, well-defined in many. Okay. Well, the well-postness, so people, as I mentioned, were make sense of the Cauchy problem, or looked at the Cauchy problem first in a very setting. It took until 19, and Jacques-Briard showed the well-postness of the Einstein equations. I'm going to write down only the Einstein vacuum. So far, it has been generalized to hold for most interesting coupled Einstein matter fields now. So what she showed is we have some initial data which satisfies the Einstein vacuum equations or coupled matter fields of them. So then there exists satisfies the Einstein equations, and with h into m being g bar and second fundamental form symmetric and k the second fundamental form. Then Jacques-Briand showed next result in 1969, and you see a long time period to actually come up with nowadays the well-postness results. So the next result of Jacques-Briand and Kerr. Well, really, give you an overview. This is the, let's say, really the clean well-postness result, but that other people contributed as well. And actually, certain things were a source of confusion, so the different invariance. So a lot of people confused at the beginning. And also people, for instance, talked a lot about, in this coordinates can do that. Now, geometry class, well, it might have certain properties that depend not. So this was not, but among not only Einstein, but David Hilbert and Hermann Weyl actually had some big comfort and others. More people and actually used, wave coordinate. And Lichnerowitz is in 39, so he shifts to the non-constant lapse. And also it was encouraged to look at that problem and look at the problem solved in the 52. So there was aware of that, and other people had their contributions. Well, there's also the characteristic initial value problem. So if you don't stay on a space-like surface, but you could give initial data on a null hypersurface. Instead of the space-like slice, you have a null hypersurface, which is your 3-dimensional manifold with responding met on that. And, you best adapted coordinates for that. And of course, provide also the responding equations for the characteristic problem. So So what people usually define certain tau shear tensor, which I call sigma here. That's what most people use. The corresponding set of equations has to be fulfilled. So the Ricciardori equation, which I write down here in this notation, and you need more equations, two more equations, which for the coefficients lambda, and another transport equation. And if you work in harmonic coordinates, you have to actually give also the corresponding equations for that. Well, the characteristic initial value problem is interesting also for many reasons. Quite often, I mean, there has been a lot of work recently in formation of black holes, for instance, when you look at incoming radiation. So that's the most natural way to look at the characteristic initial value problem for that. So in 1990, Rendell solved the local characteristic initial value problem for the Einstein vacuum equations. There's earlier work, etc. And you can think of having, well, two cones intersecting like that. One cone that starts at the point P and data on these cones. Well, now, initial data is one thing, but also when we evolve the space-time, you hope to, I mean, well, we have either some local results or some global results, and there's interesting things happening. Often you will of a certain space-time or family of space-time, but also other things can happen, like singularities, formation of black holes. So what can you say about these things? Well, first, let's start somewhere. So initial data. Well, of course, if you want to construct initial data, that's actually a very, it's a more subtle business than one might think, because if you just say you have two black hole solutions, for instance, and you add them up, so the equations are nonlinear, this is not going to be a solution of the Einstein equations anymore. However, sometimes you can make these things modify things into solutions. So there have been a lot of there's been a lot of work going into that. So the most prominent method in general is the so-called conformal method. Goes back to Lichnerowitz and James York. So what is the idea of that? It basically splits the initial data into so-called seed data and what we call the data chosen freely. The determined data, as the name says, will be obtained through the solution. Advantages. So this is if you good use solutions of the constraints, but it has a drawback for initial curvature. It works on compact Euclidean manifolds, etc., high asymptotic or high, and works in certain near CMC. If you have small mean, go away from that. If you have non-CMC data, it behaves very badly, and David and now also other people showing that. So there's
what does that mean when CMC show?
All of it this way, right? And you have uniqueness of the solution, etc. Go away from CMC.
So what you call seed data? How do you make the choice?
Which one?
Well, use data. There's some. How do you make the choice then?
In the
CMC case.
Well, you can do that, right? So.
Well, I'm just worrying about it's too much.
No, I think you can do that.
Well, I don't know.
Well, you have to. So it works. You can choose it the right way.
Works
but
means what? Means you can do a good estimate, or you just good.
You get right.
Well, no, you can propagate on. You may.
That's a different question again.
Well, good data also means that you can do well.
Yeah.
That is necessary.
That's a different question.
Okay.
So another thing, which then also shown to be the thing, is the so-called conformal thing, going back to York. David Maxwell showed a method. So, well, suggesting a generalization, the conformal method, to replace this thing by something he introduces and calls it. So when you look at that, it looks very complicated, but it's been certain things in a better way, or making. But this is really something which is. Then, of course, we have gluing method. Corvino and Schön have some here case with the Schwarzschild by Corvino. They looked at the non-time symmetric case with exterior. So the any here of the constraint equations, and for any bounded open interior here, new solution the original inside this U, and identical to a subset of whatever you take Schwarzschild or Kerr outside. And then there is other work by Krushel, Eisenberg, Matteo Pollack. Start with a pair of the constraints. And you choose a point in each, and you have production on this connected default. Ones away from the gluing points. And it's been shown that's well for initial data, let's say, for a lot of different kinds, asymptotically Euclidean, etc. And yeah, you need to do some work there on some. And most matter fields can be coupled to that. There's other developments later, maybe the late Carlotto and Schön. There's more things to say about Let me say something about and momenta. So if you think about the space of your space, the most definitions are the energy, linear, and angular momentum, ADM, Arnovit, Daser, and Misner. Here are the definitions. So you can say, well, first of all, why this is interesting. Think about the gravitational field. At one point, it can be transformed away. So how do you define energy in a field? At one point, you can gravitational field. So to think about it, well, you could go quasi-localized. So you can integrate it, for instance. Or another way to look at the mass that's here at infinity in a space-like slice, and this is for the energy. We can define linear and angular momentum for certain type of flat manifolds. For that's medium definitions. Well, they have been around for a long time. And energy, well, when we completion, what we understand is null infinity. So if you what is null infinity, you have to go here, and maybe you have black holes which propagate and are sent out. They travel along null hypersurfaces. So we have null surfaces. And gravitational radiation will at some point reach our time goes to infinity. And the interesting thing is the Bondi. We can define the Bondi mass up there for local mass, like Cauchy mass, or the mass that Yao and Wang have. The local mass, you integrate locally here, you go up to null. It should tend to the Bondi mass. So this work, Metzner and Sachs. And the famous work, of course, of the positivity of the by Rick Shane and Xing-Tung Yao in 81. And then independently we have the work by Ed Witten with a different method. And Bondi case then she's positive. So it's one of the major theorems in this area. Well, positive mass theorem tells us, we assume some Cauchy three-dimensional space-like hypersurface, which is complete and satisfies some non-negativity of the energy density. And the Schwarzschild in mass m, then the mass is positive. So zero only if and only if this here is a space-like slice of Minkowski space. There have been some generalizations to higher dimensions by these people. And so let me connect now to the Penrose inequality at some point. So what's the Penrose inequality? So first of all, there have been proofs by in a time-symmetric case by Usken, Illman. And interesting enough here, Gauch, Yang, and interesting relation, inverse mean curvature flow Hawking mass. So first of all, let's look at the Hawking mass. So this is in one notation, we can write it down like that. So we take an integral over 2 surface, where h here is the mean curvature of the surface, and so s here is the surface area as absolute value, and we can define the Hawking mass like with when you look at this family of surface inverse mean curvature flow, that one of 5 closed surfaces, 3-dimensional Riemannian manifold. So this satisfies the inverse mean curvature flow if the following is true. Normal, with the speed being just the reciprocal mean curvature. And what they found, Gauch, these are connected and satisfy the inverse mean curvature flow. Then the mass of this surface is HT bar has non-negative scalar curvature. And this is actually very useful in order to bound the total mass m in terms of the Hawking mass s. So curvature flow may not exist with some given initial data. So that the break wanted to show that, well, we can actually take solutions of this flow with all the key properties. And this is what the Riemann-Penrose inequality for single black hole by them, Ray showed or proved this Penrose inequality for multiples. So what did Penrose conjecture originally, and what's the Penrose conjecture? So initially he conjectured the following inequality. So he wanted to relate the ADM mass m to the area of any event horizon in an S flat space-time by this inequality. And of course, when you look at that, the area of the event horizon, this depends on the whole solution of the event horizon. So this is only possible to prove when we know the full space-time. So maybe we should reformulate this a little bit. So we can reformulate this in terms of quantity here that can be computed from local information only. So from initial data sets for the Einstein equations. So here is the Penrose conjecture as we write it down. So if you have an initial surface, HT bar k, which is asymptotically flat, well, of course, satisfying the Einstein rings, with a total mass m, whose outermost apparent horizon, I'm going to tell more about those in a moment, S has total size, and we did J, the energy and momentum density of the matter fields, the energy condition that should hold, then D be rewritten like that, in terms of mass m and total surface. And it's true if and only if this is a spatial Schwarzschild manifold.
So event horizon, but
Oh, this is
he was trying to use it to validate the cosmos.
probably, yeah.
So there's not much we can do.
Yeah, I think so. Yeah. So this is the way it's also in the time symmetric case you say you have these results, but the general case is completely open still. Well, talk about trapped surfaces a little. What does that mean? So, well, if I have a manifold 1 and symmetric G in plus 1-dimensional space bigger than 3 or equal, so let's look at the sphere of dimension 1 or a submanifold, and so well can look at normal directions to that and look at future directed null by outgoing and incoming null cones, these things. So let me introduce something to talk about trapped null cone. And outgoing field L and field L bar. So, the second fundamental forms over here. And the null accelerators or the mean curvatures of theta minus, and I can write down the trace of chi as equals to that, this guy. So what does that mean? It means the divergence of the outgoing or incoming light rays. And now what is a trapped surface? Well, a trapped surface we have if both of them are negative. So especially if we concentrate on the outer one, so if that is negative as well. So this is a surface that we call trapped. Now, closed trapped surfaces, here's the official definition if you want. So we have a closed trapped surface which is characterized in this setting that by the fact that the trace of chi is actually negative on S. And here the famous theorem by Penrose, similarities or incompleteness, so saying that a space-time which is a developed initial Cauchy hypersurface which is not but complete, and you have some of the energy tensor of matter, that the initial hypersurface contains a closed trapped surface. So then M, the space-time that comes such initial data, is not null-geodesically complete, so it's not null-geodesically complete. So in particular, this maximal development of such data is incomplete. And that's an interesting result, right? So that we get an incomplete space-time. So there's more discussion later. There's more to say about that. I'm going to say more about that later. Let me say a little bit about on the geometric side of this and talk about marginally outer-trapped surfaces, so-called MOTS. That's an interesting thing being studied also nowadays. So recall, if S is a trapped surface with both these theta plus and minus negative upward direction. So this is negative as from the formation, we call this outer-trapped. If the theta plus is equal, we say that S is marginally outer, call a marginally outer-trapped surface, so-called MOTS. So here are a few remarks. So if in a time symmetric case, a MOTS is simply just a minimal surface. It's actually also useful in Shane Yao's proof of positive mass theorem. And if you take the cross-section, the event horizon in an asymptotically stationary black hole space-time, where the dominant energy condition holds, then this is going to be an outermost MOTS, so the intersection. And outermost MOTS also arise at boundary of the trapped region. So this is also work by Anderson, Metzger, and Eichmeier. So here is another picture. So if you have a stationary black hole space-time, so the cross-section of the event horizon are MOTS, really. In a dynamical black hole space-time, so these MOTS typically occur inside the event horizon. So that's some facts that we know. So one version of Hawking's classical theorem of black hole topology would be the following. And I'm staying in 4 dimensions, 3 plus 1 dimension. So in a 3 plus 1 dimensional space-time, satisfying some suitable energy condition, the surface is topologically a 2-sphere. Now we know dimensions, other things can happen. And here are some interesting generalization. One theorem by Galloway and Shea, this manifold of dimension n, where n is greater. This is an initial one which is in an energy condition. So then the of dimension n minus 1 is in this manifold. Then this positive scalar circumstances. Okay, let me now jump to another topic. So there's a few I would like to talk about. So gravitation. So we have heard, of course, maybe two weeks ago, that Lydia detected gravitational waves from supposedly about a black hole. And so what are gravitational waves? So on this side, there's also some interesting mathematics and some geometric analysis that has been done, and it's interesting to describe that. So first of all, a gravitational wave we can describe as the Kerr wave. And they travel at the speed of light. And if you go back to this picture, if you think here, the waves travel at the speed of light, infinity, where we are sitting and do our experiments. So we would like to that models this kind of thing. So you plug in large data here and I understand what the radiation field looks like. About that, so that often you do a stability, or you show a global solution for some initial data, smallness of the data to some global solution, but quite often, like in the Quasilocal Energy, the smallness and just look at the asymptotic in large data, and you still have a good small asymptotics. Of course, the Bondi mass loss formula ingredient give you a very short overview who contributed and had this interesting relationship with gravity 2000, and he was kind of meaning. Other people like Eddington, Einstein himself, waves, and I already pointed out, always assumed you have an analyticity, see the propagation properties of the equation. Then in the 1960s, there have been a lot of mention, but something interesting that I would like to point out is the Bondi energy and the peeling properties of the field. So Bondi energy, so again, pioneering studies, people, so like Bieri, Robinson, Bondi, Sachs, etc., and Penrose then for the peeling properties also. So there's a lot of studies that went into that. And the Bondi energy, or also then the Bondi mass loss, is really important to study radiation. Well, in hypersurfaces, I mentioned a little, solved the local crack problem in that sense. Surfaces play a crucial role. And there's another interesting property. So maybe if you don't work in GR, maybe you heard people talk the field, etc. So what does that mean? There's controversy in that, but maybe I'm going to see just things about it. What do I mean by that? So if you have Newman Penrose with a so-called full, so this means that if you look at how does your field look like here, so you can look at components of the space-time. Curvature components have a certain type of decay; they peel. So one component R or R squared, etc. They derive a full peeling picture that for these components. And Quasilocal Energy, that is peeling. They have peeling for some of the components, but not for everything. So they derive those components of the Riemann tensor, but not for all. There has been a lot of discussion going too much to ask for physically, and or if it's something natural or not. It makes a lot of things actually much simpler if you assume that. Anyway, so the Quasilocal Energy model, you can say, well, there are these two pictures, and you can say, well, let's ask for something interesting. So a specific curvature component, which has less peeling in the Quasilocal Energy picture than in the Newman-Penrose, so they don't get the full peeling of that component. So one specific curvature which is coupled to the shear chi-bar, so to the radiative amplitude, with other words. So this is the chi-bar shear that I introduced. So these two things are connected. Now if you look at that and see, well, if peeling had to be fulfilled, so this means that this, in the past actually, this shear has to vanish. And if you look at this data, if you look at this as generic initial data of a problem, this is not physical anymore. You can come up with spacetimes where they have this property, but if this vanishes, there's not a general physical solution. This is some very special circumstances. So that suggests that the full peeling is probably too much to ask for. But still, in order to solve the whole problem here, one needs to really investigate a little bit further the Cauchy problem. What do I mean by the Bondi mass? I talked about, haven't written it down, so maybe just let me run. So here's the Hawking mass again in the other notation, trace chi-bar. The Bondi mass will be the limiting mass when you have the Hawking mass, for instance. You keep U fixed and you let T go to infinity. That's the limiting mass at null infinity. Well, and there's the Bondi mass loss formula. So if you now take derivatives with respect to a function that can parameterize your null infinity here, so then you get the Bondi mass loss formula, and that's related to the so-called Muse function. And in the Einstein vacuum case, you can write that in energy. So this is the Muse function, if you like. And so this is a limit of this shear that I showed you. And the Bondi mass loss is basically an integral over the sphere at infinity of this thing. Now you can write down an energy of this type. So you integrate this Muse function from minus to plus infinity, where U lives up here. And then F divided by 4 pi can be looked at, or is the total energy which radiated away in a given direction, solid angle. Okay. Well, let me also mention the gravitational waves. I've worked on this a little bit with different co-authors, also Jan, etc. Not in tech in a few days. So I picked up this memory effect and showed that in other fields to whisper translations and maybe other fields. So what's that? And the interesting thing is, well, if you think of gravitational waves and an experiment like you have 3 test masses here. So same distance from 2 to 0 and from 0 to 1. And the source of your wave is in this direction, and the waves come into your plane. If that's this direction, then you will only have movements of this test masses in the horizontal plane. And the thing is that you would like to detect, well, when the wave train is passing through, you have, well, the space-time is changing. These masses live on their geodesics, so the distance will be changing. And the question is, what happens after this gravitational wave train has passed? Well, the claim is that there will be a permanent displacement that we call a memory effect. So what's that? And actually, I talked to a few people working with LIGO. They would like to see that also in LIGO. There are other detectors which might be better designed for that, but there might be a chance to see that also with LIGO. So let me say what the people who worked on that. So in 1974, Soldovich and Polnareff, for the first time in a linearized frame of the Einstein equations, found that a permanent displaced memory. People thought it has to be an equation. That's not quite this. The Chrysodoulin nonlinear setting of gas equations, there is actually much better. This thing here was believed and never detected, and we have a memory which is much bigger. And for a while, people thought that it's just a linear and nonlinear version of the same thing, but with David Garfinkel, we showed that these are 2 different things. The ordinary and the null memory are not the same thing. So there are contributions. So if you have other fields like electromagnetic fields and neutrinos, they contribute to this displacement of test masses. Okay. And so maybe I jump through that. So also, maybe that's an interesting thing. So there's also an electromagnetic effect. So what we have to do to understand that, again, for this radiation, so the radiation field, well, lives out here, so to say. And in order to understand that, we need to really see what the geometry looks like, what's the analysis that lives up there. And interesting enough, so we found also that in the purely electromagnetic case, without any relativities, just Maxwell equations, we also have an analog of these 2 types of memory. What you would have is a residual kick of charge test masses, not a permanent displacement. So one thing to think about, well, if you think of electromagnetic radiation, so if you want to detect that, so these detectors absorb energy from the wave. And the flux of the energy goes like r to the minus 2, and the sensitivity also falls off like r to the minus 2. In terms of gravitational waves, the sensitivity falls off like 1 over r, but this has only to do with the fact in one situation, the motion of the particle, you really add, and in the other one, that would. Okay, so in that sense, the permanent changes that occur in the gravitational case would be a displacement, and in the electromagnetic case, a kick. So let me talk about quasi-local energy now. So I'm jumping through different topics here. So as we said, energy is a big problem in GR to understand. So we know of things, but still in general, there's a lot more to be understood. So to understand also, for instance, what's the ADM energy momentum, and we have the null definitions. But we would like to understand, let's say, what's going on. We have a natural quasi-local mass or definition. And, well, we have a few definitions now. The quasi-local energy depends on the gravitational field configuration, of course. And we like to have a natural way of defining a quasi-local mass that tends to the ADM of the corresponding limits. And there's a few masses around there. Yeah, I don't know, there's still what's mass. So why quasi-local mass should have? First of all, certainly such a quasi-local be non, well, 0 and ambient tend to the ADM and Bondi limits. And, well, it also should, if you collapse things to a point. And in that connection, so at some point, let me also forward check by Thorne. So he claimed that horizons form concentration of matter in a small region. And that was proven by Shin and Yang in a general setting. Well, again, quasi-local mass, so why should it be interesting? So here is just I write down only the Hawking mass, and there's other things I could mention. Again, in the definition from the beginning. So there are all these different masses. So Bartnik has a definition which looks good, but which is not so practical to work with, for instance. And we know that Yao and Wang and also Chen have been working a lot on the new mass. So there's more to come, hopefully, there. I could say more about that, but maybe in the last few minutes I want to talk a little bit more also about stability and singularity, showing singularity questions in relativity. And also something that I should mention are the cosmic censorship conjectures in that mission. So we have the cosmic censorship conjectures that you may have heard of if you don't work in the field, that Roger Penrose came up with. Well, what's the motivation? You can think of, let's say, if you think of this geodesic incompleteness that we heard of earlier, can we make this disappear if we perturb the initial data, or is this something generic? So that's the motivation, basically. Or can we at least say, well, if we cannot make it disappear, can we hide the incompleteness inside black holes? So the conjecture, which is the weak cosmic censorship, goes as follows, and you will find different formulations. There's many formulations of this out there. So one way to say this, for generic asymptotical flat vacuum data, the resulting vacuum spacetime has a complete future null infinity. So that's one claim, the weak cosmic censorship. And if you think of it, you could look at the toy model. A toy model would be a spherical symmetric field, or Einstein scalar field. And the analog of this weak cosmic censorship was found there, or is crucial here. So Quasilocal showed that basically you can find some naked singularities, but they are unstable. So you could have naked singularities also, but they are not stable. Okay, the strong cosmic censorship conjecture written down as follows. So Einstein, again, vacuum initial data. Solution spacetime determined extended as a suitably regular Lorentzian manifold. Again, this is a very vague formula exactly. I can give you maybe a few hints. Well, basically what you can think of generically, the future is determined by the present. So that's maybe one way to think about it. So again, what are issues? So Penrose had some physical came up with that. So one thing is that you have a blue shift, which might be a possible mechanism for infinity. So Penrose showed, what he said, this could cause blow-up along the Cauchy horizon in linear perturbations, for instance. And let's say if you look at the nonlinear theory, so you could expect nonlinearities to dominate, and blow up actually happens before a Cauchy horizon can even form. So that could also be a problem. So the idea here is that for generic dynamic solutions of Einstein equations, the causal picture would go back to Schwarzschild. Anyway, so that. So let me maybe in the last few minutes singularity. So I have certain types of initial data. I would like that no form in the future. What I would like to have, let's say, stability of my solution, or you would like to understand on this form. Feynman showed in 91 that so for perturbation Minkowski spacetime for a complete solution of the Einstein equation, so complete again along if you have initial data, which is also asymptotically flat in certain and in weight all the smallness of etc. So under the small assumptions, so this was proven then, called that's a stability result. So there were generalizations of this result in various directions and by many people. Ask for as well, this is the Minkowski space. That you perturb around Minkowski space, what's the next ask about as well? So a Kerr black hole with momentum, and this is one of the big hot topics, perturb another Kerr solution. Does that happen? So here, this is which is known as the non-wide open data set, which is some parameters where this is the angular momentum and the mass of the black holes. Then the resulting spacetime has a complete future null infinity, such that the metric here remains close for all time, and moreover is asymptotically settles down to another Kerr solution in some uniform way with the corresponding decay rates. So if you look at that, this formulation indeed does imply the statement of weak cosmic censorship in some neighborhood of Kerr. And interesting enough, so this is the full conjecture, but what have people done or known so far? So before you go and look at the nonlinear problem, you would better understand the linear problem, or even a simpler thing, look at the decay of the wave equation on some Kerr background. So we can look at three statements of stability, basically, or we could. So one is looking at linear mode stability, so saying that you have no growing solutions of mode time. Then linear stability, meaning that all linear perturbation localized initial data remain bounded for decay to linearized Kerr. And then Mr. Conjecture just showed you which. So there was some interest on mode stability by people. A related problem, as I said, to study is look at the wave equation on a fixed black hole background. So for this case, versions of linear stability on Schwarzschild were proven by these people. So in the last years, been going on, so many people worked on that, have the wave equation on some. So it's a research, but we can some findings are as follow of the wave equations on some suffix. So they remain bounded in decay inverse polynomially to zero. So that's one thing. In the extreme, also the linear case arises where in which that was not captured instability, you have some blow up in some setting here. Picture. So, generic energy of the horizon, and it goes as follows. The resulting Cauchy horizon is similar as any continuous metric extension will fail to square integral stuff in a neighborhood of any point. That's one formulation. And this is kind of an inextendability statement, if you want. And it says that the extensions cannot be interpreted as weak solutions of the Einstein equations. And again, if you want to think about this conjecture and as an inextendability statement, so one consequence is that the formulation that Christodoulou gave about the strong cosmic censorship would then be true in a neighborhood of the Kerr family. So these cosmic censorship conjectures are very much related to these questions. Okay, so we have in the Einstein-Maxwell case, so these people had some interesting results here also, that for any asymptotically Euclidean spherically symmetric initial data with non-vanishing charge and forming a black hole in the development, you can say that the maximal globally hyperbolic development admits now a non-empty null surface across which the metric can be extended as a C0 metric, but the curvature and Hawking mass blow up. So you can extend a C0, but certain quantities blow up, and no square integrability of the Christoffel symbols. Well, there's still a lot more questions to ask for, something else to point out. I don't have much time left. So Luke last year found something interesting, namely that the maximal developments of certain sets of some, let's say, general characteristic initial data contain so-called weak null singularities. So that's an interesting feature that he showed last year. I'm going to stop in a minute or so. So you can also ask, so what happens for more generally in black hole formation from gravitational collapse, etc. So maybe that's one of the things I'm going to say in the last minute only. So there's also a breakthrough result about black hole formations, and other people now followed up on that, and also Yoon Bin and has related work here. So what about black hole formation? The other question, you do want to have singularities. So in the realm of the Einstein vacuum equations, Christodoulou showed that, well, if you have enough energy concentrated in form of gravitational waves coming in the Einstein vacuum case, a black hole will form. So that's the Einstein vacuum case, pure concentration of gravitational waves, that you have a black hole. First you have a closed-wrapped surface and then a black hole. And, well, it's a large proof again, and so some ideas of the Minkowski stability are used with a new idea of this, what they call a short pulse ansatz, so a specific form of the initial data that you need. And there were results, of course, Kahneman and Rodnjansky generalized that, and then many other people also have some generalizations of this work. And probably I should mention also the black hole uniqueness theorem. So, well, what does that mean? So quite a few people, or let's say Hawking and other people here, talked about this in the analytic setting. And what does it mean here? So the black hole uniqueness without analyticity was then proven by Alexakis, Ionescu, and Kleinerman, meaning that if you have a stationary vacuum black hole that satisfies some regularity assumptions and is sufficiently close to a Kerr solution, it has to be that Kerr solution. So this was only understood in the analytic setting and has been resolved recently for more general spacetimes. Okay, probably I stop here. There would be some cosmological questions to ask about, but I only gave you a very brief overview of highlights of these last 100 years and connect to some recent research. I think there would be much more to say, but let me stop here.
Questions? I have a question.
Yeah.
So what are the features of gravitational wave solution in different dimensions?
Oh, well, people looked at that also. I mean, it's certain things you can, well, certain things you think should should be not too different, but I don't know if people study a lot of very specific features, let's say, that depends a lot on the dimension. I mean, the way your curvature decays, etc., or your space-time, certain quantities should decay, of course, is very different also. But
is there still memory effect in different dimensions?
I don't know if anybody having looked at that. It's a good question. Maybe one should look at this.
I'm interested to do a compactification case.
Yeah.
Pretty sure it's still there. Should not be that much different. But on the other hand, if the compactification is larger, maybe you can see some effect.
I mean, in physics, sometimes people talking about beyond standard model, they say like start with a higher dimensional model. They talk about the compactification of gravitons.
Oh.
But if there's no such gravitational wave solution.
Oh no, I don't say it exists. Well,
what do you gravitational?
But this is a different thing.
Even in 4 dimensions, we don't have any sort of which you can explicitly know. It's all numerical. So far.
So the graviton is something that particle physicists like to talk about, but there's no such thing known in mathematics.
More questions? No, let's send Lydia again.